In my ongoing lecture series on extraction of natural products, in the previous few lectures, I started with the basics and fundamental of extraction process. That is, what is an extraction? What are the parameters, or I will say what is the mechanism by which a solvent enters into the sample matrix and solubilize the constituent from the plant matrix, and then it diffuses out into the bulk solvent. So what are the steps involved in this whole process? Then I discuss what are the parameters with respect to the extraction procedure, with respect to the matrix character or the sample characters, vis-a-vis solvent characters that will affect the extraction process or efficiency of the extraction process or the yield that is obtained by that extraction process. Then I discuss about the conventional extraction techniques or the old extraction techniques like maceration, infusion, decoction, refluxing, soxalate extraction, and so on and so forth, wherein I discuss the principle behind these extraction procedures, the parameters that can affect the efficiency of these extraction procedures, and then I also discuss about the modifications that are done in these extraction process with respect to the laboratory scale and also with respect to the industrial scale equipment or the procedure. Then I started with certain modern extraction technique, or which are also known as greener extraction technique, because they require less energy, less solvent consumption is there, and in return we get a better yield in comparison to the conventional technique, or if not better then equivalent yield in comparison to the conventional or the old techniques. And in those methods I discuss about ultrasound assisted and microwave assisted extraction techniques, wherein I discuss their principle, their instrumentation, their parameters that affect their extraction efficiency, their application in the field of natural products, and so on and so forth. So friends, in continuation with the lecture series, today I am going to start with another modern extraction technique which is known as pressurized solvent extraction. Now I will be discussing this technique on the same lines which I have discussed the previous technique. That is, first I will explain you what is pressurized solvent extraction technique, on what principle this technique is based, followed by what are the types or the modes of pressurized solvent extraction, what kind of instrumentation is involved in this technique, what are the factors that affect the overall efficiency of this technique, and in the end I will be discussing about the applications of the pressurized solvent extraction. Now before I further dwell into PSE or pressurized solvent extraction technique, I would just like to focus on this figure which shows the development or the change in the approach of solvent selection in different extraction technique. In yesteryears, or rather I will say at present also, we use organic solvents which are considered to be not environment friendly, because we know that there are certain side effects of these organic solvents and a lot of energy is required in order to evaporate them and when we want to concentrate our extract. Then once we realize the detrimental effects of organic solvents, we shifted on to eco solvents which were less toxic in comparison to the organic solvent like glycerol. Further, we improved our extraction processes by using natural solvents which were having very less toxic effects in comparison to the previous two classes, such as we used vegetable oils or alcohols. We further improved the selection of the solvent by incorporating supercritical fluids, and this I'll talk about in detail when we'll discuss about supercritical fluid extraction. But for example, carbon dioxide, which is a gaseous substance, we applied carbon dioxide, we subjected carbon dioxide to certain pressure or temperature conditions by which the properties of carbon dioxide change and it act as a solvent. Further, we modified towards more greener solvent like water, and we further modify the extraction procedures by which we can use water as a solvent, because we know that water is the most safest solvent, most cheapest solvent which is available at present. And eventually we made the extraction techniques, we developed the extraction techniques in such a manner that we can extract the desirable secondary metabolites, we can extract the plant matrix with a specialized techniques wherein we don't require solvent to extract, and such extraction techniques we call them as solvent free extraction. So this was just an idea that how over the period of time we change or we modify our extraction procedures in order to use more and more greener solvents which are environmentally safe, which are safe to the user as well. So coming back to pressurized solvent extraction or PSE, now this concept was first introduced in 1995 by scientists who were working at Dynex Corporation. Now Dynex Corporation has been overtaken by Thermo Fisher in 2010, and now it's a subsidiary of Thermo Fisher Corporation. Now they proposed the concept of pressurized solvent extraction in 95, but it was only in 1996 when Richer and his group, they coined the term accelerated solvent extraction, or if I say in simple words, then PSE or pressurized solvent extraction is also known as accelerated solvent extraction. But accelerated solvent extraction is a trademark name for which has been registered by the Dynex Corporation. For our convenience, throughout our lecture we will be interchangeably using these terms PSE or ASE. Now during the same time, Hawthorne along with his research group, they were also working on this same concept, that is pressurized solvent extraction, but in this technique they were using water as a solvent. Now when water is used as a solvent in PSE, that technique becomes subcritical water extraction. Now there are different names given to pressurized solvent extraction. One I have already discussed, that accelerated solvent extraction, which is a trademark name for registered by the Dynex Corporation. Now PSE is also known as pressurized liquid extraction or pressurized hot solvent extraction. It is also known as high pressure solvent extraction, subcritical solvent extraction, superheated liquid extraction, or enhanced solvent extraction. Now why so many names have been given to this single technique? This is because in this technique we subject the sample towards solvent extraction at very high temperature and high pressure conditions, and therefore these are known as high pressure or pressurized hot solvent extraction techniques. Now the temperature and pressure conditions are so adjusted that they form the subcritical values for that particular solvent, and therefore this technique is also known as subcritical solvent extraction. Now since the liquid is heated, and it is not only heated up to its boiling point, but it is heated much above the boiling point of that particular solvent, and therefore such technique is also known as superheated liquid extraction. So this is how this technique got different names, different nomenclature, but pressurized solvent extraction technique or accelerated solvent extraction technique are most widely acceptable term for this particular technique. Now the major advantage of ASE is that it is an acceptable method by US Environmental Protection Agency under method 3454A for extracting various pesticides, herbicides, polyaromatic hydrocarbons, polychlorinated biphenyl compounds from different matrices. This technique has also been approved by European and Chinese government for the determination of the pesticide residual content, for determination of the lipid content, flavor content or flavor profiles of different food items, and various other additives that have been added to the food contents. So this is the importance, or this is the significance of ASE, that this technique has been widely accepted by the regulatory agencies for specific purposes. In addition to that, this ASE allows us to use those solvents which can be used for the soxalate extraction, because in my one of my previous lectures I told you that soxalate is a technique which has been widely accepted by the regulatory agencies for extracting out specific type of constituents. So the solvents that have been approved for the usage in soxalate extraction of those secondary metabolites, same solvents can be used using accelerated solvent extraction or pressurized solvent extraction. Now we move on to the principle of PSC or ASC. Now, as I told you that under this technique we subject the sample matrix or we subject the solvent at high temperature and pressure conditions, which help in improving the overall extraction efficiency. Now the question is, what is the level of the high temperature? What is the limit of the high temperature? Now normally it is considered that we take the solvent to a temperature which is far more higher than the atmospheric boiling point of that particular solvent. Now since we have to boil or we have to take the solvent to a very high temperature above its atmospheric boiling point, we require high pressure to keep that solvent into liquid form. Crux of the principle of this technique that you have to subject the sample mixed with the matrix to a higher temperature which is far above its atmospheric boiling point, and we apply high pressure in order to keep the solvent in the liquid state. And the temperature generally ranges from room temperature to 200 degrees Celsius, and generally the pressure range is kept at 35 to 200 bars. So this is the basic principle of high accelerated solvent extraction or pressurized solvent extraction. Now the selection of the temperature or pressure, it will be largely governed by the nature of the matrix, whether the matrix is soft or hard. Obviously if the matrix is soft, then temperature and pressure conditions can be kept towards the lower side with respect in comparison when the sample matrix is quite hard. Vis-a-vis, the particle size of the matrix also govern the temperature and pressure values which one has to select for the extraction process. Presence or absence of moisture also affect the overall extraction efficiency, and it has been observed that presence of moisture has a negative impact on the overall extraction yield. So depending upon whether your sample is fresh or whether your sample is dry, you have to adjust the temperature and pressure conditions. Obviously we are going to discuss the effect of temperature and pressure in detail when we will discuss about various factors that affect the extraction efficiency. Then comes the hydromatrix. Now hydromatrix is nothing but a type of diatomaceous earth which is responsible for the absorption of moisture if it is present in your sample or the matrix. Apart from absorbing moisture, hydromatrix also act as a dispersing agent. So we can also add various dispersing agents. Hydromatrix is one example. Glass beads are also used as dispersing agent in ASC. Now what these dispersing agents do, they fill up the voids or the empty spaces that are left when the sample is packed in the extraction cell. Now once those voids or empty spaces are filled with dispersing agent, they reduce the overall consumption of the solvent, and they also help in bringing the uniformity of the extraction process. Because if empty spaces are left and solvent pockets are formed there, then that particular area will have more contact with the solvent in comparison to the other areas, which causes the non-uniformity of the overall extraction process. So this was in a brief overview that how you have to go for the temperature and pressure selection during this technique. Now we move on to the modes of pressurized solvent extraction or accelerated solvent extraction. Now this technique largely occurs in two modes, static and dynamic mode. Now as their name indicates, static means when the solvent is in contact with the matrix for a specified period of time, whereas in dynamic it means which keeps on moving. So the solvent keeps on flowing through the extraction cell, and every time the drug comes contact with the fresh solvent, which further increases the extraction process. Now we will discuss each mode in detail. So coming on to the static mode of PSC or ASC. Now this mode is considered as less versatile in comparison to the dynamic mode in terms of flexibility and possibility of coupling to other analytical processes. Now it has been seen that in static mode, since we have to keep the solvent and the matrix in contact for for a specified period of time at a particular temperature and pressure, you cannot immediately move the extract to the analytical process. So first you have to complete the extraction, then only you can subject the extract to the analytical process. Whereas in case of dynamic process, since solvent is continuously flowing through the extraction cell, that flowing solvent can directly enter into an analytical process wherein we can analyze the extract for the type of the constituent or in order to quantify the desirable constituent. Still, this technique is widely used because large number of commercial extractors are available in the market, number of them from Dynex, one is from Bookie also. So lab scale as well as commercial extractors from different manufacturers are available for the static mode. But with the passage of time now, various dynamic mode extractors have also been developed, but these dynamic mode extractors are at the laboratory level right now. So what are the steps that are involved in static accelerated solvent extraction or pressurized solvent extraction? First and the foremost is the treatment or the pre-treatment of the sample, or in simple words if I say preparation of the sample for the extraction process. So if you have a solid sample, obviously we have to dry the sample, we have to reduce the particle size of the sample, that is the size reduction or the grinding process, and then we subject that grinded sample towards sieving. Now the sieving helps us in getting the homogeneous type of the sample, because you have to pass the grinded sample through a specific sieve size. So whatever sieved material you obtain, that will have almost uniform particle size. Now uniform particle size will help you in uniform packing of the extraction cell, thereby causing a uniform overall extraction process. And then if you have a liquid or a solid liquid mixture sample, then obviously you have to first filter the sample through centrifugation or by any other appropriate filtration method, or you can subject the sample towards drying or freeze drying before you fill your sample into the extraction cell. Next step is the loading. Now once your sample is prepared by subjecting it to various drying, grinding, sieving or filtration techniques or processes, then next step is to fill your extraction cell with the sample. Now extraction cell has two metallic filters that are placed at the top and at the bottom, or in other words at the input side as well as on the output side of the extraction cell. We call these metallic filters as metallic frits. Now once you pack your sample and you apply the frits on the extraction cell, then these frits or metallic filters have a tendency to get clogged over the period of time. And once these frits or the filters get clogged, then the overall pressure, back pressure, increases tremendously over the period of time, which will impact the overall efficiency of the equipment that is involved in this process. So therefore, in order to prevent the clogging of these metal frits or metal filters, we cover them with a layer of cellulose filter, or we add a layer of a dispersing agent in order to prevent their clogging. Then you can also add dispersing agent into the extraction cell. I have already discussed that these agents fill up the voids or the empty spaces or the empty pockets that are formed whenever sample is packed in the extraction cell. And various dispersing agents that can be used are diatomaceous earth, hydromatrix is one such example. You can also use anhydrous sodium sulfate, that will further help you in absorbing the moisture. You can also use the inert material like sand in order to fill those empty voids or the empty spaces. Another advantage of static mode is, if any kind of derivatization of the sample is required during the extraction process, then specific reagents that are required for its derivatization, they can also be added into the extraction cell. So when the sample is packed along with the derivatizing agent and that extraction cell is subjected towards specific temperature and pressure conditions in presence of solvent, the sample may undergo required derivatization and you can extract out the derivatized sample. Next step is the filling. So once you have packed or loaded your matrix or the sample into the extraction cell, next step is the filling up of that extraction cell with the solvent. So once you fill that extraction cell with the solvent, the extraction cell is then completely tightened so that there is no leakage of pressure or the solvent. Now before you pack solvent into the cell, again there are two methodologies by which you can pack the solvent in the extraction cell. One is you can preheat the extraction cell before filling with the solvent, or you can fill the solvent and then heat the entire extraction cell with the sample and the solvent to the required temperature or the pressure conditions. The later technique, that is heating of the extraction cell after filling it with the sample and the solvent, is generally preferred. So once the sample is filled in the extraction cell, the mixture or the extraction cell is allowed to equilibrate for 5 minutes at desired temperature and pressure conditions. So this allows the solvent to penetrate into the matrix. This allows the decrease in the viscosity of the solvent due to increased temperature, and in addition the higher pressure helps in ease of its penetration into the matrix. Increased temperature also helps in the solubilization. So overall equilibration occurs during these 5 minutes. So the next step is the extraction. So once the sample is loaded, extraction cell is filled, it is exposed to the desired temperature and pressure conditions. The extraction cell is allowed to stand at those specified temperature and pressure condition for specified period of time, and during this time the entire extraction takes place. So once the extraction is complete, the extract is collected in the collecting vessel, and after that the cell is purged with the nitrogen gas. Now purging of cell can be done by two methods. One, I have already told, purging done by the nitrogen gas, and second is you can rinse the extraction cell with the solvent, with the 60% of the volume of the extraction cell with the solvent that has been used for the extraction. Now why this purging or rinsing or the washing of this extraction cell is being done? Because once the extraction is complete and you collect the extract in a collecting vessel, then still small amount of the solvent remains in the extraction cell that has been absorbed by the plant matrix. So in order to remove the traces of those solvents, we either purge the cell by high pressure nitrogen gas, because we know nitrogen is inert, so it will not cause any kind of interaction with the constituent, or we can rinse the extraction cell or the sample with roughly 60% of the total volume of the extraction cell. That also prevents the carryover between the consecutive extraction for most of the applications. Now in this picture you can clearly see the setup of a static mode extractor. You can see different solvent reservoirs and they are attached with a pump. The pump helps these solvent to fill the extraction chamber or the extraction cell, which is placed in a oven or a thermostat equipment to apply the required temperature conditions. And below the extraction cell is a static wall which is closed for the time period for which the extraction has to be carried out, or extraction takes place during the specified period of time, and for that specified period of time this static wall is closed. Now what happens is, if we go into the equipment design for the static ASE, I'll just take back you to the picture. So what happens is, once this pump purges or pumps the solvents into the extraction cell which is already filled with the sample, this extraction cell is then subjected to the prescribed temperature and pressure conditions, and the static valve, as I told you, remains closed. So once that specified time period for extraction is over, the static valve is opened. Once the valve is opened, pressure is released, a pressure gradient develops, and the solvent or the extract that is present in the extraction cell flows into the collection bottle. So once the flowing of the solvent or the collection of the extract occurs, again the purge valve is open, which allows the nitrogen gas at specified pressure to enter into the extraction cell, thereby causing washing of the extraction cell or the purging of the extraction cell to remove the remnants of the solvent. Again, those remnants are mixed with the main extract in the collection bottle, and then the extract is subjected to the post extraction steps, like if drying is required, we dry the extract under vacuum, or we can subject that extract to the analytical process. So friends, in the next lecture I will discuss about the equipment design for the static mode. Thank you.